In this section we're going to be looking at sketching regions. Now at the moment we're only going to be looking at mainly circles and arguments in the regions that we sketch, but we can expand this in a little while to include ellipse and hyperbola as well. But I've written down here three different examples, and at first glance they look very similar. In fact, all of these are the same. The only difference is the equality or inequality that I've used over on this side. So the first example is sketch z plus 1 minus 2i equals to 3. And so from our last section that we looked at, we know that this is a circle. Put it in standard form, so it's z minus z1. And we know then that the center of the circle is that z1, which is negative 1 plus 2i. Notice it's the opposite of that. Negative 1 plus 2i is the center, and we've got a radius of 3. So for all of these three questions, they're all going to be about circles. Center there, radius 3. So let's quickly draw that. Negative 1 plus 2i is going to be there. There's our center, and this particular circle has a radius of 3, so we go up to 3, down 3, across 3, and back 3. So we're going to be back at minus 4. And so now we could draw our circle in like that. Okay, so that would be the correct answer to question number 1. Question number 2 says sketch the same thing. Now remember this magnitude, the absolute value here, is telling us this is a distance. It's the distance between z and this fixed point. So z can move anywhere. If z was the tip of my pen, z can move anywhere in the first one, anywhere so that it is 3 units from the fixed point in the middle. So the only place my pen could move would be exactly around the circumference of that circle. But now look at this question. This question says the distance between z, my pen tip, the distance between z and my fixed point can now be anywhere up to 3. Anywhere up to 3, so it could actually be 2, or it could be anywhere between 0 and 3. So my pen could now stray its distance from this fixed point here. My pen could now stray into anywhere inside the circle, and it would still be satisfying the equation where it's less than or equal to 3. So for question number 2, the region that I'm actually sketching, the region could be anywhere inside the circle, because the distance between z, the condition was the distance between z and this fixed point must be less than or equal to 3. So my point could be anywhere on the circumference or anywhere inside, and so we shade the region that we require. Okay, so this was 1 and 2. In example number 3 here, you'll notice that it's a little bit different. Now I'm not going to go to the trouble of putting in all the numbers, but basically we've got a circle that looks like this. You would need to do it accurately, but I'm just trying to make the point here. In this case we've got a greater than sign, so the distance between z and this fixed point, my center of my circle, now has to be bigger than 3. Now, can it be equal to 3? No. So the circumference of my circle is I actually can't include, but I do have everything outside my circle. Could be, I could have my radius bigger than 3. It could be anywhere out here. And so what we do is we shade outside. But we've got one problem. How do I show that the radius of 3 is not included? Well, what I should have done, and I jumped in too quickly, and it's very easy to do this, but I should have, how we say that the boundary is not included is that we dot the boundary. Okay, so whenever it's just a greater than or a less than sign, it means that that boundary that you've drawn is not included, and the only way we've got of showing that is to dot it. So I recommend that when you draw these, you draw them in pencil. Just in case you forget, you can dot your boundaries later. But in any case, you can do what I've done, and you could actually put an arrow and say dotted boundary. But better if you remember from the start. But when you're drawing these, it's very easy, like I did, to quickly draw it and then realize that it should be dotted. Once again, the reason it's dotted is because it wasn't equals to. It was just greater than. This one, the boundary was included because it had an equal sign. Okay, as well as the less than. Okay, so in summary, if it's not equal to, dot the boundary. If it is equals to, then you include the boundary. The next region that we want to have a look at sketching, and you may remember some of this from earlier in the year as well. Sketch, I'll do a couple of examples here. Arc Z between 0 and 2 pi on 3. Now have a close look at this. Have a close look at this. Arc Z, remember the argument of a complex number is its angle from the positive x-axis, positive real axis. So arc Z here has to be greater than, reading this way, arc Z has to be greater than or equal to 0, but less than, notice, not equals, less than 2 pi on 3. So when we come to draw that, arc Z equals 0 is right here, the positive real axis. 2 pi on 3 is going to be somewhere out in this region. Okay, 2 pi on 3, because this would be 3 pi on 3, or pi. So 2 pi on 3 is going to be somewhere out here. Notice it's not equal to. So the argument, the angle, can never be equal to 2 pi on 3. So to do that, we dot it. Label it. There's 2 pi on 3. And so the argument of our complex number can be anywhere between greater than 0 and less than 2 pi on 3. So the region that we require is anywhere inside that space, and so we shade it in like that. Once again, because the 2 pi on 3 is not included, we need to dot that boundary. Okay, a slightly harder one of those. Let's look at this. Arc Z, or Z minus 2i, has to be greater than or equal to negative pi on 4 and less than 3 pi on 4. Okay, so when we come to draw that one, now this is a little bit more complicated than this one. This one was centered at the origin. In this case here, our argument is now shifted. The angle that we're looking at, the whole thing is shifted up 2i. You remember doing those shifts from previous work. So this one is now shifted up 2i. So here it is. That's like our origin now, if you like. And so our angles, everything is relative. If you can imagine in your mind, there's the x-axis now. Everything is relative to this point up at 2i, because it shifted up 2i. So negative pi on 4 from this point will be an angle coming, remember negative angles come back this way, so negative pi on 4 would be an angle coming out down there at negative pi on 4. Because it was an equals to as well, I could include the boundary. The 3 pi on 4, well, we know 3 pi on 4, here's 4 pi on 4, okay, straight across. So 3 pi on 4 is actually going to be straight out the other way here. 3/4 of pi will be up this way. And you realize what I've just done? I drew a solid line, but in fact it should have been dotted because it's not equals to. So I actually need to dot that line. As you can see, very easy to forget. Need to dot that line in there so that that boundary is not included. So now we want everything between minus pi on 4 all the way up to 3 pi on 4. So in fact this is the region that we are going to sketch. Lastly, let's have a look at a combined region. So sketch. Magnitude of z less than 2 intersecting with, and that notation you may not be that familiar with, but that's the intersection, means combined. You may have seen that in probability in Maths B. Intersecting with arg z greater than minus pi on 2 and less than or equal to 3 pi on 4. So we want to sketch that full region. So we notice here that we've got a circle intersecting with an argument region. So what we do first of all is just sketch both of these. Now this one is actually you may just not recognize that. Remember remember the standard form of a circle is z minus z1 equals the radius. Well, in this case z1 is 0 because we've got z minus 0, or which we don't write, is equal to our radius of 2, except in this case it's a less than. So this is a circle, very simple circle, centered at, in this case, the origin. Z1 is 0 plus 0i. So if we come to sketch that, we came to sketch it, it's a circle with a radius of 2, 1, 2, 1, 2, 1, 2, okay. Now I'll try and think ahead this time. Notice that the radius can never be equal to 2. It can only ever be less than 2. So we know that the boundary must be dotted. So we dot that boundary for the circle. Now if I was just sketching the circle, I'd now shade in the inside because it's less than, and we would be done. Except in this case we're just going to hold off our shading for a moment. Let's do this argument now. The argument, the argument centered at the origin as well with this one. It has to be greater than negative pi on 2. Well, here's negative pi on 2 down here. It has to be greater than negative pi on 2. Notice it's not equal, so I'm going to need to dot negative pi on 2. And less than or equal to 3 pi on 4. There's 4 pi on 4. We know 3 pi on 4 is out this way. it's equal to, so I could draw a solid line. This is 3 pi on 4. And so the region there, according to this part of the question, the region that I'm requiring is everything from minus pi on 2 around to 3 pi on 4. So normally I would sketch this whole region out here. And for the circle I'd be sketching the inside. But for this question, where we're actually sketching the intersection, in other words, where does this region and this region combine? Okay, intersect can also mean and. Where does this region and this region combine? Well, if the argument is all out here and the circle is inside the circle, then the region combined is that space in there. So that's our combined region for the circle and the argument.